Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for the BSc Honours Physics students. We have been going through a course of lectures on optics, and in the series of lectures we had earlier, they were on the geometrical optics. Then we moved on to the wave optics. In the case of wave optics, one has to obviously go through the phenomenon of interference, and obviously from interference you move on to the Michelson's interferometer. In the last lecture we were discussing about the geometrical construction of the Michelson interferometer and also the principle of the Michelson interferometer and the condition under which you will be getting circular fringes. So, the contents of the lecture 23 will be as follows: estimation of the difference in wavelength of the 2 light sources, derivation for the expression for the wavelength difference, determination of the thickness of a thin transparent plate using Michelson's interferometer, obtaining the refractive index of a gaseous medium, and the standardization of a meter. I told you in the last lecture, you get circular fringes. When do you get circular fringes using a Michelson interferometer? When the 2 mirrors M1 and M2, if they are kept perpendicular to each other, you will be getting circular fringes. On the other hand, if you make one of the mirrors to be slightly inclined, you have got mirror M1 here, M2 is not exactly perpendicular to M1, the angle that is separating these two is not 90 degree, slightly inclined, you get what is called a wedge shaped film. You get an air wedge because the effective path difference will not be will not be 0 or lambda. It will be you get extra path traveled by one of the beams because the mirror is slightly inclined. Therefore, when 2 mirrors are tilted, they are not exactly perpendicular to each other, and therefore the mirror M1 and the virtual image M2 prime are not parallel. In this case, the air path, that is the medium through which light is travelling, that is namely medium is the air path between them is wedge shape. It is something like what you had in the case of air wedge. So, the fringes appear to be straight. So, you will be getting straight lines or straight bands. If one of the mirrors is moved, the fringes move across the field. The position of any particular bright fringe is taken up by the one next to it. So, as I told you, if the mirrors are inclined, you have got M1 is fixed. You know very well that among the two mirrors which we are talking about, one of them is fixed. The other can be moved either forward or backward, and also it can be moved slightly along from this plane. It can be made to assume a inclined position. Therefore, M1 is fixed. Here again you got a fixed position for the mirror M1. On the other hand, the image obtained from the mirror M2 prime, from the M2 you get the image M2 prime, that makes an angle with respect to the fixed mirror M1. So because of that, you will be getting the films with arc-like images. Then for a particular angle, you will be getting the straight bands, something like you got in the case of air wedge. The fringes can be counted as they pass a reference bar. You can move the eyepiece and you can count the fringes. If M fringes move across the field of view, when M1 moves through a distance d, then d will be m lambda by 2, or lambda will be 2d by m. And these fringes are called localized fringes. And regarding applications of Michelson's interferometer, it has got several applications. The first one is the determination of wavelength of a monochromatic source. Then the wavelength difference between two sources. You take the sodium vapor lamp. Is it a monochromatic source? Strictly speaking, sodium vapor lamp is not a monochromatic source. For all practical applications, it is considered as a monochromatic source, but strictly speaking, it has got a doublet. You call it a sodium yellow doublet. One is having wavelength 5890 angstroms, the other is having wavelength 5896 angstroms. Therefore, if the wavelength of the two sources of the two lines are different, the wavelength difference can be determined using the Michelson interferometer. Then the thickness of a glass plate can be determined. The refractive index of a glass plate can be determined. Not only the refractive index of a glass plate, you can have air or some gaseous medium within a container. The refractive index of the medium also can be determined. And lastly, the meter can be standardized. You know what is 1 meter. The meter can be standardized using the Michelson's interferometer, or the interferometer serves as a instrument for standardization of meter. So we start with the measurement of wavelength of a monochromatic source. The interferometer is used to determine the wavelength of a monochromatic source. The source is kept at S. The mirrors M1 and M2, you know the position of the mirrors. I need to repeat them once again. The mirror M1 is moved either forward or backward. The circular fringes appear or disappear. I told you in the last lecture, the center of the first one will be dark because the path difference is lambda by 2. If I add another lambda by 2, how do you add another lambda by 2 path difference? By moving the mirror through a distance lambda by 4, the movable mirror, it is moved through a distance lambda by 4, it is equivalent to introducing additional path difference lambda by 2. So, an additional path difference lambda by 2, that means you are adding half wave. Earlier, it was lambda by 2. What is lambda by 2? The path difference lambda by 2 means the crust is meeting a trough, there will be darkness. If I add another lambda by 2 with the lambda by 2, that means it will become lambda. Lambda means what? The crust is meeting a crust. The crust of one wave meeting the crust of the other wave, the two waves separated by the wavelength lambda. If the wavelength separation is lambda, a crust is meeting a crust, or a trough will be meeting a trough. In both cases, there will be constructive interference. Therefore, the fringes will be made to become bright or dark depending upon how much distance through which the mirror is moved. Now, as the mirror is moved through a known distance d and the number of fringes disappearing at the center is counted. I told you, whenever the mirror M1 is moved through a distance lambda by 4, you are introducing a path difference of lambda by 2. So, from brightness, you will go to darkness. Okay. And if you want to get again brightness, then you have to again move through lambda by 4. What is that move? The mirror should be moved through lambda by 4. So, depending upon the distance through which the mirror is moved, you can go from bright to dark band, dark to bright, and so on. So, dark rings, bright rings, dark rings, and so on. So, you can count the number of fringes which are disappearing at the center, that can be counted, and it depends upon the distance through which the mirror is moved. Suppose D1 is the initial thickness of an AR film between the mirror M1 and the image of M2 corresponding to the bright fringe of order M1, and D2 is the initial thickness of the AR film corresponding to a bright fringe of order M1 in the same position. Then 2D1 can be written as M1 into lambda, and 2dn is equal to mn into lambda. 1 is the order of the fringe, and n may refer to the nth bright band. 1 refers to the first bright band. N refers to nth bright band. By subtracting the above equations, you get 2d1 minus d1, d2 minus d1. 2 multiplied by d2 minus d1 will be mn minus m1 into lambda. That turns out to be 2d into n lambda. That means your d2 minus d1 is taken as d, and m1 minus m1 is equal to capital N. That means your lambda will be 2d by n. Or in other words, the wavelength of the source can be determined by an expression of this kind, where d is the thing that matters. D is the distance through which the movable mirror is moved, and n is the number of rings that are disappearing. Then the determination of the difference in the wavelength of two light waves can be obtained as follows. If a source of light consists of two wavelengths, lambda 1 and lambda 2, as I told you, the sodium vapor lamp is the case where the two wavelengths are there. Even though it is called a monochromatic source, it has got two wavelengths, because the wavelength that separates the two lines are only 6 angstroms. They differ slightly. Then the two sets of fringes corresponding to the two wavelengths are produced in Michelson's interferometer, where two sets of fringes will be occurring. So, you will be seeing at the same time bright and dark due to one set, another appearing bright and dark, and bright can be made to coincide with bright, and dark obviously will coincide with dark, and so on. By adjusting the position of the mirror M1 of the interferometer, the fringes are made very bright. In this position, the bright fringe due to lambda 1 coincides with the bright fringe due to lambda 2. When the mirror M1 is moved, the two sets of fringes get out of step because their wavelengths are different. When the mirror M1 has been moved through a certain distance, the bright fringe due to the first set will coincide with the dark fringe due to the other set, and no fringes can be seen in this case. Again, by moving the mirror M1, a position is reached when a bright fringe of one set falls on the bright fringe on the other, and the fringes are again distinct. This is possible when the mth order of the longer wavelength coincides with the m plus 1th order of the shorter wavelength. So, you have let m1 and m2 be the changes in the order at the center of the field when the mirror m1 is displaced through a distance d between the two consecutive positions of maximum distinctness of the fringes. 2d can be given by an expression of this kind, m1 into lambda, that will be equal to m2 into lambda by 2. What is m2? You should remember m2 is the order of the fringe that is coming from the second source. M1 is the order of the fringe coming from the first source. They differ by one bright band. So if lambda 1 is greater than lambda 2, then M2 will be M1 plus 1. So at this point we will have a break. Welcome back to the break. We have been talking about the method which could be used for determining the wavelength difference between two sources of light whose wavelengths do not differ by a large magnitude, employing the Michelson's interferometer. Here you come across finally an expression of this kind: 2D is equal to M1 into lambda 1. That will be equal to, what is the M1 and M2? You had your M2 is equal to M1 plus 1. We had 2D equal to M1 into lambda 1, that is M2 into lambda 2. And M2 is nothing but M1 plus lambda. By combining these simple expressions, you get 2D equal to M1 plus 1 into lambda 2. And here you got M1 into lambda 1. So equate these two things. You will be getting M1 will be equal to lambda 1 will come in the denominator. So your lambda 2 divided by lambda 1 minus lambda 2, or 2D will be lambda 1 multiplied by lambda 2 by lambda 1 minus lambda 2. That is your 2D, because your M1 is here, right? M1 being substituted by an expression of this kind. So lambda 1 is here, lambda 1 multiplied by lambda 2 by lambda 1 minus lambda 2, that will be equal to 2D. So your lambda 1 minus lambda 2, what is lambda 1 minus lambda 2? That is the difference in wavelength between the two light sources. And lambda 1 minus lambda 2 may be 6 angstroms, as in the case of sodium vapor lamp. That becomes equal to lambda 1 multiplied by lambda 2 by 2D. But you don't know lambda 1, lambda 2. So what you do is you take the average of lambda 1 and lambda 2, taking lambda the mean wavelength of the two wavelengths lambda 1, lambda 2. The difference delta lambda is given by an expression of this kind. Delta lambda is lambda 1 minus lambda 2. That will be equal to your lambda 2 and lambda 1. You take the mean. Therefore, lambda 1, lambda 2 will be lambda square by 2D. That lambda is the mean value. Therefore, the final expression for the wavelength difference between the two light sources whose wavelengths do not differ by a large value will be given by an expression of this kind, where you find delta lambda equal to lambda square by 2D. Okay. Then we pass on to yet another application of Michelson's interferometer, thickness of a thin transparent sheet. This is similar to what you had in the case of air wedge. You interposed a thin sheet or a thin wire between the two glass plates. Then you got a wedge shaped film and you are able to determine the thickness of the wire. Similarly here, the thickness of a transparent sheet, the sheet can be introduced in the path of the light beam, because you are introducing a sheet that will give rise to extra path difference. The refractive index come into the picture. There will be extra path difference. So from the extra path difference, you can determine the optical path differences, right? And therefore, let a transparent sheet of thickness T and refractive index mu be inserted in the path of one of the interfering beams of the, you have got light ray going to the mirror M1, another light ray going to the mirror M2. In one of the light beams, you introduce the transparent sheet. It should be transparent because you have to see the light ray going and coming back. A transparent sheet of refractive index mu the optical path of that beam increases because of the sheet. Optical path increases means what? The time taken by the light ray will become larger. The optical path will be, so the path difference will be there. It becomes mu t instead of t. You all know that you have to have mu t instead of simply t. Now the time taken in air is t. Time taken by light ray to travel through a medium of same thickness t will be mu into t, because denser medium, right? Time taken will become larger. So the increase in the optical path is mu t minus t, or you take this t outside, or mu minus 1 into t. That should be equal to, if this is equal to n lambda, you have to find out by interposing this transparent sheet how many fringes have moved. The number of fringes which have been moved can be measured by means of the micrometer, by making the micrometer screw, or making the crosswire by looking at the crosswire, how many fringes have moved can be seen, or you make use of white light to see effectively how many fringes have been moved. So, since the beam traverses the medium twice, the extra path difference between the two interfering beams, instead of mu minus 1 into t, you should have 2 times mu minus 1 into t, that is the effective difference in the distance between the two light beams. If m is the number of fringes by which the fringe system is displaced, by interposing the thing, you can see how many bands have been shifted. So that will be m bands are shifted. Therefore, you will have 2 into mu minus 1 into t equal to m lambda. So, when monochromatic light is used, it is difficult to distinguish the sudden shift in the fringes. When you interpose the thing, all are yellow in color. So, you cannot see the movement at all. You will see something is happening, but the exact number of fringes which have been shifted because of the introduction of the glass plate, because of the introduction of thin plate, it may be a glass plate or some other plate, that cannot be exactly measured. Therefore, you have to use white light. It is also not possible to count the number of fringes shifted. The difficulty is overcome by using white light first to locate the central dark fringe. You locate the central dark fringe before the introduction of the glass plate, and it is made to coincide with the crosswire of the telescope, and then introduce the thin sheet that introduce the path of the beam. Position mirror M1 is adjusted till again a dark fringe of 0 path difference coincides with the crosswire of the telescope. The distance d through which the mirror is moved is noted. So, you have to use white light to see the exact distance through which the number of yellow fringes which have been shifted. So, that for that you have to make use of white light. The distance d through which the eyepiece is to be moved, or the crosswire is to be moved, is noted. Using that, you have to now, white light is now replaced with the monochromatic light, and the mirror M1 is moved backward slowly, and the number of fringes contained in D is found. The thickness T is obtained from the relation T is equal to the number of fringes M comes in the numerator, lambda, the wavelength of the source, monochromatic source will come in the denominator, 2 into mu minus 1 will give you the thickness of the plate. But mu should be known. For the thin plate, transparent plate that is being introduced, the refractive index should be known. That you have done already the experiment which can be used to determine the refractive index. So, therefore, only if the refractive index of the plate is known, then T can be determined. Or if T is known, mu can be determined. So, same kind of procedure can be adopted now for determining the refractive index of gases. So far, in the experiments which we have seen under optics, either you talk of Fresnel biprism or air wedge or Newton's rings, we have never spoken about determining the refractive index of a gas. Now comes the Michelson's interferometer, the very important instrument using which the refractive index of a gas also can be determined. What you have to do is, you take a container. The container is made up of glass plates whose refractive index should be known. The refractive index of the glass plate using which the container is made, it should be known. Then pump in the medium, pump the air or some other gas into the container and keep it there. Now the light ray will be passing through the glass plate as well as the medium, as well as you can have methane gas or some other gas, carbon dioxide. Now that gas can be kept at any pressure, any desired pressure. The refractive index will depend upon the pressure also. So the refractive index of the gas can be determined along with the path difference caused by the glass plate. There will be path difference caused by the medium. You measured you had water as below the lens of a Newton's sixth experiment. You had below the lens, you had water. Similar to having water, now you have got a gas kept in a container, and the refractive index mu of the gas, and L is the length of the tube. You have a tube, length of the tube. In this tube, you have got the medium, you have air or carbon dioxide as the gas. Then the light ray is made to pass through. It passes through the glass plate as well as the gas. If M fringes cross the center of the field of view, then 2 multiplied by mu minus 1 into L. L is the path length of the glass tube. That is equal to M lambda. That is a condition that you come across here. Now, knowing the length of the glass plate, length of the container, and by seeing the shift in the number of fringes, as you did in the experiment earlier, the shift in the number of fringes that has been caused now when you introduce the container with the gas. You can do without gas and with gas. Then the difference in the number of fringes that have been shifted, that is your M. Knowing your M, knowing L, M and lambda, mu can be calculated. This is an important experiment which has been used to determine the refractive index of gas, not only the gas at any particular pressure, for a series of pressures, as to how the refractive index of a gas changes as a function of pressure. It is a uniform, you have got a straight line kind of thing. The linear relationship has been observed in the path of the rays of light going towards M1. A tube containing air at atmospheric pressure is introduced, and the fringes are obtained in the center of the field of view. In that case, the refractive index of air at various pressures can be determined. So, the refractive index of gases can be determined by having the gas in a container. First, the tube is completely evacuated, right? Then the fringes which are crossing should be determined. Then you introduce the gas. Then once again do the thing. The path difference is introduced between the two interfering beams is 2 into mu minus 1 into L. That will be equal to M lambda. Lambda comes as M divided by lambda into 2L will come here plus 1. Let me now go to the summary part of the lecture 23. The procedure for determining the wavelength difference between two light waves whose wavelengths are adjacent to each other is explained. The method of determination of wavelength difference between two sources employing Michelson's interferometer is described. The way the experiment is to be carried out for evaluating the thickness of the thin transparent medium is outlined. Michelson interferometer can also be used to standardize a meter. You have the questions. Explain the method of determining the wavelength of a monochromatic source using Michelson's interferometer. Give the mathematical expression for evaluating the wavelength difference between two light sources whose wavelengths differ by a small value. Question number 3. Describe the procedure used to determine the thickness of a thin transparent medium using Michelson's interferometer. How does one determine the refractive index of a liquid? With this, we come to the end of the lecture 23. The standardization of meter, how the Michelson interferometer can be used to standardize a meter, will be discussed in the next lecture along with the other things as given in the syllabus. Thank you.